Okay, in this video we're going to be looking at the stiffness metrics for truss members in the local access system. So let's say that right over here we have a truss member. Let's take a pen. Let's say this is a truss member and let's call our truss member A, B. So there is an A point and an B point. Now let's consider that there are some forces working on it. For example, if I say there is a horizontal force on this member, let's call that horizontal force XA. And there's another horizontal force right over here. Let's call that horizontal force XB. Similarly, let's say that there is a force on the vertical direction. We're going to call this force YA. Similarly, we have YB here. Okay, so we have the forces set up here, and let's assume that the length of this truss member is L, and the modulus of elasticity for this member is E, and the cross-sectional area of the truss member is A. Okay, so from the previous lecture we have learned that the stiffness, dk, is equals to EA by L. So we're just going to write that up, EA by L. Now let's say that let's call this this axial stiffness. Since this is axial stiffness, that's not denoted by K. This time I'm going to be denoting it by Sx. So here Sx is actually stiffness in the axial direction, so we're going to be calling Sx axial stiffness. Okay, so if I just erase this real quick, there you go. Okay, so let's move on. Now let's say that the truss member, we already know that the truss members don't have any flexural or shear stresses because trusses don't have bending moments or shear forces on them. Alright, in that case we're going to neglect the shear stiffness and the flexural stiffness as well, because there are no shear or flexural stiffnesses. Now let's say the displacement of displacements of A and B. Let's just draw the displacements of A and B real quick. Let's see, let me take the black color here. So let's say this is the displacement at A, for displacement at A. This is the pin support right here on B. There you go. For A, there you go. For the A, the XA force, we have already learned that force is equal to stiffness into deflection, right? So instead of XA, we're going to write up SX and UA, right? So SX UA, this is the force right over here, and let's say that this deflection is UA equals to 1 unit deflection. Let's consider there's a unit deflection here. So if the force is being applied here, another counter force is going to come up over here at the point B, right? So we're going to write up that force, and that force is going to be equals to this particular force. That is why it's going to be Sx UA. Okay, all right. Now when we're going to consider force on the B point, this is A again and this is B again. This time the force is actually acting in this direction, so this is Sx UA, this time let's call it Sx UB. Okay, so this is Sx UB on the B direction, and right over here, from here to here, let's call it the UB. Unit deflection UB is equals to 1. Okay, so since the force is being applied here, another counter force is going to come up over here, which is going to be Sx UB. Alright, so we have two kind of situations going on here, and we have two more situations for the force YA and YB. Let's draw them up. So let's say this is B, this is A right over here, and this is the vertical deflection VA. Let's say VA is 1. Similarly, we're going to have another one here, or we can draw it up on the other direction. Let's draw it up in the other direction. This is going to be similar to the other one. So there we go. This time this is A, this is B, and here we have VB, which is 1. So we have this 4 scenarios, so we can now write up equilibrium equations for these scenarios. So for starters, let's write the equilibrium equation of fx in the A joint at the A point. So that's going to be supposed to be 0. We can write up the force here is XA, as we have seen from here, XA. So just going to write up XA. Now we know that force is equals to stiffness into displacement. So at the A joint, here you go, A joint, we have one force that is acting towards the right direction, which is SXUA. So we're going to write up SXUA, since it is in the right direction, it is positive. Then we have this displacement right over here. Since there is no stiffness, because this is a pin joint, let me take another color. There you go. As we know, the truss joints are pin joints, so they allow rotation. So when the force, the vertical force hit it, it actually moved the truss member. So there is no resistance. Since there is no resistance, there is no stiffness. Okay, so since there is no stiffness, what we're going to do is we're going to write a plus, right? So stiffness here, Sx is 0, 0 into Va plus. Let me write up the equations in a different color. Let's take this color. Okay. Alright, great. Right after that, at the A joint, in this figure, you can see that there is a negative force here, SXUB. So instead of plus, this is going to be minus SXUB. There we go. Right for that, plus here at the A joint, there are no forces. Right over here at the B joint, sorry. Here at the B joint, there are no forces. There at the A joint, sorry, this is the A joint. At the A joint, there are no forces, so we're just going to write up 0, or what we can do is we can write up 0 into VB. You can do that as well. Okay, so this right here is our equation 1. Now, we're going to do the same thing for Fy at joint A. Is equals to 0, is equals to YA is equals to, here there are no vertical forces, so there is going to be 0 plus 0 plus again 0, because there is no stiffness. So since there is no stiffness, if I multiply VA into 0, there is going to be 0. If I multiply VB into 0, there is going to be 0. So just 0, nothing but zeros. So this is our equation 2. Let's call this equation 2. Now moving on to equation 3, which is Fx at B joint. So this is 0. Here we have XB, and here, since this is the B joint, we have negative Sx UA minus Sx UA, then plus 0, then plus Sx UB. This time the Sx UB is plus because this is toward the right direction at the B joint. Okay, plus 0. So this is our equation 3. And finally, for our fourth equation, we have y b equals to 0. So we have yb equals, is going to be similar case as ya. So at B direction, there is no upward force right here, no upward force here, and here are upward forces, but the forces are making the truss member move, so there is no stiffness. So stiffness is 0, and stiffness multiplied by deflection here is also 0. So 0 plus 0 plus 0 plus 0. So right now we have developed 4 equations. And next we're going to be converting these 4 equations into matrix form. So let me just take another page so we can put these equations into matrix form. Okay, this time, okay, let me just, okay, let's just go to the next page right over here. So these are the equations. We're going to be writing these equations up in the matrix form. The best way for you to follow the lecture would be to write up the equations and then follow along as I put them in matrix form. So right now we're going to take a pen. Let's take a pen. Now we're going to write up the matrices. So here, let's say this is going to be the first matrix, and here we're going to put in the, here we have the SX, then we have the 0. This isn't actually 0, this is 0 into VA. So you can write up VA here if you want, but since this is ultimately going to be 0, we are writing up the 0. We're not going to put the deflections here, we're just going to put the stiffnesses here. So this is going to be the stiffness matrix right over here. So SX, then we have 0, then we have minus SX, and then again we have 0. This is from equation 1. Now from equation 2, we have 0, 0, 0, 0 stiffness. Now from equation 3, we have minus SX stiffness, then 0 stiffness, then SX stiffness, and then 0 stiffness. And from equation 4, we have 0 stiffness in 4 cases. So this right over here is our stiffness matrix that can be denoted with K. This stiffness matrix, and let's put an L at the top. This L is meaning local axis. Okay, this means local axis. So this L stands for local axis. Now we have the stiffness matrix. Now along with the stiffness matrix, we're going to place in the displacement vector. So here we go, the displacement vector field. There you go. Here at the first location, if we go back, you can see at the first locations we had UA. There you go, UA. Then we have VA. Then we have UB, then we have VB at the 4th location. So that is where we're going to replicate. At first we had UA, so here we have UA, and here we had VB, so sorry, not VB, VA. Then here we have UA, UB, we have UB, and here we have VB. There you go, VB. So this is the deflection. This is the deflection vector. Now, if we multiply the stiffness matrix with the deflection vector, we're going to get the force vector, right? Because this is K into U is equals to F. This is F or P, whatever you want to call it. So this is what we have seen in the previous lecture, right? Okay, so here if we put in the force vector, the force vector is going to be XA, then YA, then XB, and then YB. So here we can call this PL again, and the L stands for local axis. So here we had our formula KL into UL equals to PL. So this is the stiffness matrix for 2D truss members in local axis. Okay. And if you come here, these are the forces, XA, and we have YA, XB, YB, which is placed here, XA, YA, XB, YB. Alright, so that is it for this video. Thank you very much for watching.